Like my new hat? It's a solar-powered, air-conditioned golf hat. Now what about this thing? It's the world's only combination hot dog steamer and bun warmer. And this handy device keeps champagne corks from becoming unguided missiles. These bizarre gadgets all serve a function. What makes them funny is that the functions they serve are absurdly narrow. Some of the statistical formulas we've been working with lately are a lot like these gadgets. Our Z formula for finding a confidence interval, for instance, is great if you know the standard deviation of the population. But that's hardly ever the case. In this program, we'll learn how to get around that problem. We'll learn about T procedures, which are used to calculate confidence intervals and do significance tests when the population standard deviation is unknown. We'll see that T procedures are based on T distributions, which are similar to normal distributions. And we'll learn T procedures for paired comparisons, an important kind of comparative study. Let's see why the Z formulas we've been using are like over-specialized gadgets. Here are the familiar Z formulas: the Z statistic for tests of significance and the corresponding Z formula for finding a confidence interval. As I said, the culprit here is the sigma in both. That sigma represents our unrealistic assumption that we know the standard deviation of the population. Fortunately, there's an easy way around this assumption. When we don't know the standard deviation of the population, we can estimate it from the standard deviation of the sample. We call this sample standard deviation S. We can get rid of the offending sigma in both formulas and replace it with S. Of course, once we change a major component like that, we can't use Z, the standard normal distribution. We need a new distribution called T. T-tests and confidence intervals use these formulas along with the new distribution. Figuring out the exact shape of this T distribution wasn't easy. In fact, the problem wasn't cracked until 1908, when a chemist at the Guinness Brewery tried his hand at it. Making ale requires constant sampling of everything from barley to brewer's yeast. The chemist, William Gossett, wanted to save time and money by using the sample standard deviation instead of the population standard deviation. Gossett had some statistical training, and after much laborious work, he finally produced the T distributions. But when he went to publish his findings, Guinness wouldn't let him use his name. So he used the pen name Student, and the methods using his distributions are called Student's T-tests. Let's see how T distributions compare to the normal distribution we're familiar with. Here's the standard normal curve, and here's a typical T distribution. You can immediately see that it shares certain features in common with the standard normal curve. They're both roughly bell-shaped, and they're symmetrical about 0. But the T curve is broader, and its tails are higher. The high tails mean there's more probability of getting results far from 0. That's because S, the sample standard deviation, varies from sample to sample, and this variation adds some uncertainty to the results. The other major difference is that although there's just one standard normal distribution, there's a different T distribution for every sample size. That makes sense because as our sample size increases, the sample standard deviation S gets closer to the population standard deviation sigma. Large samples give more accurate results than small samples. For small sample sizes, the T distribution is, as we've seen, flatter than the normal curve. But as the sample size increases, the curve narrows and gets closer and closer to the standard normal curve. The different T distributions are specified by the sample size, and statisticians have a particular way of saying this. Instead of saying sample size, they use the phrase degrees of freedom. And the degrees of freedom for this T statistic are always 1 less than the sample size. So if your sample size is 10, you use a T distribution with 9 degrees of freedom. T procedures for confidence intervals and significance tests are very common. In fact, they're vital at a place nicknamed the nation's ruler.
The National Institute of Standards and Technology seems an unlikely place to do your shopping. But if you're in the market for a standard of reference to measure or align a material or a machine, there is no better store in the world, because from these shelves, you can buy a standard reference material for almost any application.
We have our own catalog and deal with about 40,000 different customers. From most government agencies, when you buy something, you don't get a real material. You just perhaps get a piece of paper like the certificate that goes with the standard reference material.
But here, you get the real thing, a bottle of material, its chemical content analyzed, and its constituents listed and certified. Customers from science, medicine, and industry can use the contents as a known quantity to calibrate their analytical machinery. But with over 1,000 to choose from, it's sometimes hard to settle on just one.
Well, every standard reference material tends to be a favorite. Looking at just a few of the interesting ones, we see cast irons, phosphor bronze, synthetic refuse-derived fuel, pH standards, bauxite, manganese ore, iron ore, polystyrenes, plastics, cholesterol in coconut oil, cholesterol in human serum, river sediment, urban dust, PCBs, PAHs, THC in urine, a marijuana metabolite, new mixed diet reference material, including some steak and some bread and some eggs and a little beer and wine thrown in, and all mixed up and blended, and then freeze-dried. There are others here, potassium chloride, sodium chloride. This is perhaps the world's most expensive table salt.
There's only one thing this vast array of materials has in common. Every customer needs to be sure that the values on the certificate match what's in the bottle they bought. Analyzing and certifying each and every bottle of material would be ideal, but too expensive. The challenge is to determine and guarantee the certified values for an entire population of material by analyzing a random sample of bottles from that population. The first step is to make the total population as homogeneous as possible.
They grind it and they pulverize it and they dry it and they sift it and stir it ad nauseum. When we're actually selecting which bottles are going to get analyzed in the lab as representative of the whole population, we do a stratified sampling scheme.
From a log of all the bottles in a population of the chemical PCB, polychlorinated biphenyls, Suzanne generates a randomized list of bottles which are pulled from the warehouse. This sample of PCB reference material is analyzed to measure its chemical constituents. These lab results become the basis for a statistical analysis of all the PCB bottles.
The constituent value is the mean, and what we're trying to do is assess how well do we know that mean. The uncertainty attached to that is described by a confidence interval. Most of the time, we don't know the true standard deviation of the population, and when you've had to estimate the standard deviation, the distribution that you need to use is the t-distribution. And we use the t-distribution to give us basically a multiplier to multiply times that standard deviation, which gives us then an uncertainty.
The uncertainty is stated on the certificate as a confidence interval around the mean PCB concentration. This piece of paper becomes important when the reference material is actually used as a quality control check. For example, scientists at Michigan State University are experimenting with a natural microbe that breaks down dangerous toxins in PCBs. They employ the PCB reference material to calibrate their test equipment. Then they can track the microbe's performance with accurate and repeatable measurements.
They want to make sure that their system is in control. In other words, they don't have an unknown bias. So they'll measure our material. Ours gives them a target value to make sure that they're hitting. Now, if we just gave them the mean value, boy, they'd use it as a target, and if they didn't hit the bullseye, they wouldn't know what to do. What our interval does is it tells them that with, say, 95% probability, the true value of that bottle of stuff that they're measuring falls within that interval.
We're going to use the T procedures to estimate one of the NIST's single population means. We'll start by finding a confidence interval for the mean level of PCBs. Here are the concentrations of PCBs in 10 vials of solution. The sample mean is 289 parts per billion with a sample standard deviation of 1.8. Using our T procedure for finding a confidence interval, we can plug in the values for X bar, S, and N. Now we need to find the value for T star. For this, we'll need a new table, so let's take a look at it. Here's part of a table of critical values of T. The vertical column under the heading DF is degrees of freedom. The values in the column headings represent the percent of area under one tail of a given T distribution. We look in the .025 column when we're interested in a 95% confidence level. That's because we want 0.05 of the area to be left under the tails, so the area under one tail is half that, or 0.025. And since our sample size was 10, we look in the row across from 9 degrees of freedom. Remember, we take the sample size minus 1. Doing this gives us a value for T star of 2.262. You might remember that the Z star value for a 95% interval was 1.96. So you can see that the T statistic will give us a wider confidence interval. That's the price we pay for not knowing sigma. With all our values in hand now, we find that our interval for a 95% confidence level is 289 plus or minus 1.3. You can see that, aside from using a different table and using S instead of sigma, the calculation of a confidence interval using T distributions is exactly the same as using the Z distribution. The same is true of significance tests. Nothing changes except that we exchange S for sigma in the formula and get a T statistic instead of a Z statistic. The inference techniques we've just learned are aimed at estimating the mean of a single normal population. But we can also use these methods for comparative studies, which are usually more reliable than single sample investigations. One common class of comparative study is called a paired comparison study. In one type of paired comparison study, a group of subjects is divided into sets of pairs that have been matched on some important characteristic. One member of each pair, selected at random, gets a treatment. The other doesn't. At the end of the experiment, the difference between the members of each pair is determined. The one-sample t-test applies here because we're looking at one result, the difference between the two subjects. Another kind of paired comparison study is the classic before and after study on the same subjects. One place where these paired t-tests are quite common is in the food industry.
One of the most promising products in the long search for a safe, low-calorie sweetener is NutraSweet. Used in hundreds of different foods and beverages, NutraSweet, most people agree, is the best tasting of all the sugar replacements. But maintaining a consistent taste is often a problem, since NutraSweet can lose sweetness after a few months of storage. So when working with a new cola, for example, NutraSweet researchers must make sure the prototype will have a shelf life of at least 4 months. Will this prototype meet this standard? To find out, NutraSweet's sensory evaluation team is preparing for a taste test. The beverage will be evaluated once immediately after it's been made, and then again after 1 month. The difference will be analyzed with a paired t-test, as NutraSweet statistician Tom Carr explains.
A paired t-test is a statistical test of hypothesis where you have a single sample that's measured, for instance, at 2 points in time, and it reduces to a single sample t-test when you consider the differences between the first and the second time the object is measured.
Taste your standards first and then rate your sample. Okay.
This group of 10 panelists has undergone 4 months of daily training. They are about to decide the fate of the prototype cola. When they are ready for their samples, they turn on the red light. Researchers in the kitchen are waiting for the signal. One of the most difficult tasks the panelists learn is how to quantify the enormously subjective attributes they'll be rating.
We use these panelists as analytical instruments, and like any analytical instrument, you need to calibrate them. So they're given references of maybe 5 units on the 15-unit scale, 10 and 15. And through a series of examples, they get to know what intensity is associated with all the points on the scale.
After they taste the standards, the panelists are ready to proceed. They taste the cola and rate it in a series of attributes: brown spice, vanilla, sweetness, and many others.
Hi there. Go ahead and sign in number 5. We have 1 sample.
1 month later, the panelists return. During this time, the cola has been stored in extremely warm conditions to simulate 4 months of storage under normal conditions. The taste test is identical to the earlier one. The same panelists, the same procedures, the same standards. All sources of variability besides the change in the cola have been eliminated. The null hypothesis for this t-test is that the sweetness after 1 month is equal to the initial sweetness. The alternative hypothesis is that the sweetness at 1 month is less than the initial sweetness. It is a one-tailed test, since Tom Carr is only interested in whether the cola loses sweetness over time. To test the hypotheses, Tom must first calculate the difference between the before and after sweetness ratings for each panelist, and then find the mean of these differences.
By performing the necessary computations using the means and standard deviations that we observed, we can compute the t-statistic value and then compute the probability of obtaining that value in an experiment by looking up in a table or by having a computer calculate the probability for us.
Tom found that the sweetness fell off 1 unit, a result that had a less than 5% probability of occurring by chance. This provides strong evidence against the null hypothesis and led Tom to conclude that the product had in fact changed over time.
Going back, we found that the acidity level wasn't quite right, and that would account for the more rapid decline in the sweetness that we saw. And I would imagine...
At a strategy session, the results of the taste test are discussed and a course of action is charted.
Going into an unacceptable level, even if you boost the sweetness a little bit initially.
Fine.
Researchers will change the formulation and then test the cola again to see if it retains its sweetness longer. But even then, the process is not over. Through rigorous experiment design and data analysis, any attribute of the product can be isolated, tested, and continually improved.
R&D people love to look at millions of things, and we will never stop researching a product. Using statistics, we set the boundaries very quickly, and we understand that outside this parameter we have unacceptability, outside this parameter we have unacceptability, and here's where we're going to live.
Let's see how Tom Carr arrived at his conclusion that the cola lost sweetness after 1 month of accelerated storage. Here are 10 testers' scores for the taste of the fresh soda, and here are the scores from the same testers for the month-old soda. To do a significance test, we first need to find the differences between the pairs of scores. Now we have a single set of observations that we can analyze using the single sample procedures we've just learned. To describe the differences, we first compute their mean and sample standard deviation. We find that the mean taste score dropped by 1 with a standard deviation of 1.13. We want to test the null hypothesis that the sweetness of the sodas doesn't deteriorate systematically. So the null hypothesis is no change. Mu, the mean change in the soda, is 0. The alternative hypothesis is that the sweetness decreases. Mu, the difference in the before and after scores, is greater than 0. The t-test statistic is the same one we've used before. The numbers we plug in are x bar, which is 1, mu, which we assume is 0 by our null hypothesis, s, which is 1.13, and n, which is 10. Doing the arithmetic gives us t equals 2.8. Now we need to find the p-value that corresponds to this figure. To do that, we use our table of critical values for t. Since our sample size was 10, we look in the row for 9 degrees of freedom. The table shows that 2.8 lies between the 0.02 and 0.01 critical values. That's between 2% and 1%. This means we could expect a drop in sweetness as large as we found, fewer than 2 times in 100, if nothing was happening here but normal variation. That's strong evidence that our null hypothesis is false. The sweetness of the test soda does deteriorate significantly over time. We've already seen that t-tests are valuable because they get around the requirement of knowing the population standard deviation, and they let us work with relatively small samples. It turns out that they have another benefit. They're robust. That means they'll produce tolerably accurate answers even if your data aren't normally distributed. In fact, if you have more than 15 observations, the t-test will work even for somewhat skewed data. Of course, you always have to be sure that the data come from a properly randomized sample, and you always have to watch for outliers. The robustness of t-tests, combined with their ability to produce meaningful information from small data sets, makes them particularly good in studying uncommon disorders such as autism, which affects 1 in 2,500 children.
Look how nice you look in this picture.
A mother and child, but no ordinary child, nor an ordinary relationship. 9-year-old Jossie Saavedra was born with a mysterious and devastating disorder called autism, although it wasn't apparent at first.
Can we put some music on now?
No. When she was about 9 months old, she looked absolutely lovely. She had large eyes. She was just beautiful, very healthy.
But by the time Jossie was 2, she showed the classic symptom of autism. She withdrew into her own world.
There was no real mother-daughter interaction, and I remember telling her father, I don't think she loves me anymore. I think there's something very wrong.
While this lack of interest in others is the most profound and disturbing symptom of autism, there are other symptoms: uncontrollable hand flapping, mental retardation, aggressive behavior, a fascination with objects, severely impaired language. Surprisingly, the problems develop unevenly. Autistic children seem almost normal in some areas, much behind their chronological age level in others.
Good boy, you gave me cup.
This makes education difficult. Researchers have only now begun to understand that they have to examine each part of development separately.
People have looked at cognitive development, language development, much less commonly at social development. There's some reasons people haven't looked at social development. For one thing, it's been very difficult for people to have a good way to measure it. But it's particularly important in autism, obviously, because it's one of the things that we think is most fundamentally wrong with autistic children.
Now there's a new test developed at Yale called the Vineland, which allows researchers to measure the separate components of development and document statistically that social development is what is most delayed in autism.
I'm going to do what's called the Vineland Adaptive Behavior Scales.
Because getting information from autistic children is difficult, the Vineland relies on interviews with the person who knows the child best, usually a parent. The result? Age equivalent scores for 3 separate areas of development: communication, socialization, and daily living.
She can make French braids. She can comb hair, blow dry it. She can tie things, but she does not tie her shoes. And again, there's no interest in tying her shoes.
For example, by comparing Vineland scores for a particular child, say a 6-year-old, researchers would know that the child has the daily living skills of a 4-year-old, but the social skills of a 3-year-old.
We used a paired t-test to compare interpersonal skills to daily living skills. We found a very significant difference between the autistic child's ability in the socialization area, particularly in relation to other people, and their abilities in daily living skills.
This difference within a child's development, significant at the .001 level, is not seen in any other group of children and distinguishes autism from other disorders.
Put the dryer on.
This study gives us a way to very adequately characterize what an autistic person's social development is like. That then would help us develop intervention programs that were tailor-made to that person's level. So that, for example, a person whose social skills were more like a 2-year-old might really require a rather different kind of intervention in terms of their social development than someone whose social skills were more like that of a 4- or 5- or 6-year-old.
It says here, did Jossie hit anyone today?
Quantifying the disorder is an important first step in understanding autism. Vineland scores give parents, like Edna Saavedra, separate numbers for autistic children's intellectual, social, and coping skills. They can set new educational goals for their children and realistic expectations for themselves.
Nicely. Nothing is taken for granted and nothing goes unappreciated. You learn to be thankful for the things that she can do. I'm proud of the person that she is.
The Yale researchers found a significant difference between the daily living skills and the social skills of autistic children. We can go one step further. We can estimate with 99% confidence the actual size of that difference for the entire population of autistic children. Knowing this interval can help parents and educators to set realistic goals for different areas of development. In one study at Yale, researchers measured the equivalent ages in both daily living and social skills for 22 5- and 6-year-old autistic children. The mean difference was 1.1 years and the standard deviation was 0.8. Our interval is 1.1 plus or minus t star times 0.8 over the square root of 22. Our t star value depends on what confidence level we want. For a confidence level of 99%, we need the 0.005 critical value from the table. The t star value for a sample with 21 degrees of freedom equals 2.83. Doing the arithmetic gives us 1.1 plus or minus 0.5. The interval ranges from just over half a year to more than a year and a half. From the sample mean, we now have an estimate of the actual mean difference between daily living and social skills for all autistic children ages 5 and 6. With our introduction to T procedures, we've begun to move into real-world inference. That's possible because we can now use the sample standard deviation instead of the elusive population standard deviation. We also saw that T procedures are robust against non-normality and that they'll work with relatively small samples. These are the kinds of tools statisticians use day in and day out. In the programs to come, we'll meet one such tool after another, all of them based on the concepts we've already learned.